Good evening everyone. I am Shivani Dhok and I welcome you all for the week 12 tutorial for the course of Modern Digital Communication Techniques. So like every tutorial, this tutorial will be divided into two parts. First one will be recap of the week 12 content, and that will follow the questions related to the content that were taken in this particular week. You may stop me at any point for any queries. So let's start with a recap of week 12 content. So basically this week started with channel equalization and estimation. So it was said that this channel equalization basically needs channel estimation, and this channel estimation can be based on two ways. One is data aided, another is non-data aided. This requires some additional pilot transmission so that you can get your you can estimate your channel. Then there were various ways of estimating your channel as well as estimating your data. So one of the way was your linear transversal filter, which suppose if I have z equal to xc, then I can have this e as x inverse z. So in similar way, if we have y equal to hx plus w, then estimate of h can be given as y into h Hermitian x Hermitian whole inverse. So this factor here is known as the pseudo inverse of x. Similarly, if I want to estimate this x, then I can get it as x hat equal to h Hermitian h inverse h Hermitian y, and here this component, this factor here, is known as the pseudo inverse of h, and this is known as the least squares method. Another way to do that was your Wiener filter, Yule-Walker equations and Wiener-Hopf equations. Then the mean squared error criteria was discussed. So basically it says that if I have a date something, and so what it basically says is, if that your error, so suppose you want to estimate h, and let's say your estimate is h hat, then your uh, error, that is h minus h hat, will be orthogonal to your data. So your error will be orthogonal to your data. Your data will be your signal that you are receiving, that is y equal to hx plus n. Then based on this idea, the next estimate, that is linear minimum mean squared error estimate, was discussed. So if I have y equal to h theta plus w, and this theta is something that I need to estimate, and this theta hat is given by this formula here, where this mu hat is your mean of this theta, r theta theta is covariance, and rww is covariance of this w, and so on. Another iterative way in order to get your estimate can be steepest descent. So this allows you to minimize your function by going in this direction direction opposite to the maximum change. So that is known as your steepest descent. So then wn plus 1, that is the next update, will be based on your current update minus half mu gradient of j, where j is your function that you are minimizing, and mu is some scaling factor which you can tune, or it can be also called as a learning parameter or a step size, so that you can increase and decrease it based on the need of your um, function. You may also find the optimal value of this mu, which may be based on your gradients and other stuff. After that, in order to understand the further concepts like time and time synchronization, carrier phase synchronization, and all, the next thing that was introduced were two major concepts of estimation theory, which are the Cramer Rao bound and ML estimate. So basically, when you don't know the statistics of the parameter which you want to estimate, for example, suppose I want to estimate theta from the data y, and if I don't know the statistics of these, then it becomes very difficult to find an unbiased estimate or an optimal unbiased estimate. So in such a situation, we call such an estimate as minimum variance unbiased estimate, or MVU estimate, and there are various ways to find this MVU estimate. And another thing is, this MVU estimate may or may not exist. So one such way to find your MVU estimate is given by this Cramer Rao bound. So what does this Cramer Rao lower bound tells us? So it basically gives you a lower bound on your error covariance. That is, it says that you can't go below this error covariance, whichever estimate, whichever this kind of estimate where you don't know this theta value, whichever unbiased estimate you consider, all will have your errors greater than or equal to, error covariances greater than or equal to your Cramer Rao lower bound, and that can be found only when your regularity condition is met. And your MSE, this is your lower bound, which is 1 upon I theta, which is 1 upon I theta, which is given by minus expectation d square by d theta square log fy theta. And suppose I am able to write this first differentiation of log fy theta with respect to theta in the form of I theta into gy minus theta, and this gy is your MVU estimate for theta. That is you have theta hat equal to gy, and this estimate is an MVU estimate, and it achieves this Cramer Rao lower bound, that is the lowest possible bound, and hence such an estimate is known as efficient estimate or efficient estimator. Now suppose I don't know any information and handling this also becomes very difficult. In such situations, a very naive way to find an estimate is maximum likelihood estimate, such that theta hat will be the argmax of fy theta. That is, you'll find the value of theta that will maximize your likelihood function. Now benefits of this ML estimate are asymptotically this theta hat is Gaussian with mean theta and variance as I theta minus 1. This I theta is again this Fisher information matrix which we have found here. And this we had used, ML estimate we had used to find this phase estimate, which was obtained something like this. After looking at these basic concepts, we went on to see the carrier and phase synchronization aspects. So the basic need for this carrier and phase synchronization is, at transmitter you have a clock, then at receiver also you have another clock, because you want to do your demodulation operation. You will multiply with your basis, so carrier, you will multiply with your carrier. Local oscillators, I'm sorry, at transmitters you will have your local oscillators, at receiver you will have your local oscillators. And and if we look at the receiver structure, we first of all demodulate or correlate with your basis functions, which are basically your carriers. Now when we are doing that, a basic assumption is the carrier which you are using at your transmitter and at your receiver are in phase and are using same frequency. However, that may not be the case. It may happen that your transmitter and receiver have the frequencies which differ very slightly. Also, there might be some phase delay in the uh, phase delay or some difference in phase at the clock which is at the carrier which is being generated at your receiver and that generated at your transmitter. And if we have such a situation, then it will be difficult to you demodulate, because you'll have some error terms coming up due to such unsynchronized carrier. And that's why we need to do your frequency, your carrier synchronization and phase synchronization. And in order to do that, what we need to do is we need to estimate these two things, that is frequency and phase, and we need to compensate them at your receiver. And this can be done by PAL structures or decision directed structures or squaring loop structures and Costa's loop. After that, the next thing is your clock synchronization. Again, the timing thing or the clock thing, like here, so basically you're transmitting symbols, and one symbol is being transmitted for one symbol duration. So now this definition of one symbol duration and when that one symbol duration is starting is very important, because you are sampling at your receiver end. So if the symbol duration T is different at your transmitter and the receiver, that is the clock that generates this T have some error, like let's say some t plus delta is being generated at your receiver, or t plus minus delta at your receiver, and we have at transmitter we have t. So again, you will sample at different or different locations. You won't get a proper samples. Another thing is, if there is a delay, like if it is a t plus delta thing you're having, like okay, so this is your clock at transmitter and this is your clock at receiver, these both are t. So now again you should know that this is your transmitter, this is some delay you're having at your receiver, and you should compensate at this particular thing. So in order to do that, the solutions are, you have a master clock that controls the clock at both your transmitter and receiver, becomes difficult. Again, you have your you make your transmitter to send the clock information, that is, now it is starting, this is this much duration and so on. Again, this may consume some of your data part. Another option is, your receiver will extract the clock information from on the basis of your received data. So in this process, maybe initial things may be very bad, however as time progresses it will be very easy, and you will get a good estimate of your clock. Another thing is, this third point you can do by having your ML estimate or early late gate synchronization. I'm not going into the details of these things. These are covered in the lectures, and you may also refer the books whichever are mentioned in the on the course web page for these details. However, in this session I'll focus on this part. I also saw your assignment. There are few questions which are related to Cramer Rao bound and ML estimate, and so I'll focus on this part little bit, and little bit on this part, so that you are able to solve your assignment questions and whatever questions come up in your exam, which will be next week. Okay, so if there are any questions, I'll be happy to answer. Otherwise, I'll start with the questions that I have planned to cover today. Okay, so let's start. So this is the first question. So what we need to do is, for the following, find the least square and LMMSE estimate of x if y equal to hx plus w. W is IID Gaussian with zero mean and variance sigma square. So this is what we have here. And yeah, another thing that we can assume is this x is zero mean. So let's assume that this x is also zero mean. Okay, yeah, so let's start with this least square. So what do we have? This is least square. So we have y equal to hx plus w, and we need to find x hat for least square. Now if you observe carefully, we had seen this here. So we have this y equal to hx plus w. So x hat will be h Hermitian h inverse h Hermitian y. Same thing will come here. Y equal to hx plus w. So this will be h Hermitian y multiplied by h Hermitian h inverse. So let me write it properly. So this will be h Hermitian h inverse h Hermitian y. And the next thing that we need to find is this LMMSE estimate. And how to find this LMMSE estimate? Again, we'll go back to whatever we had discussed earlier. So we have this y equal to h theta plus w. Okay, so this theta hat is mu theta r theta theta h Hermitian h r theta theta h Hermitian plus r w w inverse y minus h mu theta. So let me write this here again. So this thing will be, we need to find x hat. So this thing will be basically your expectation of x plus h into rxx multiplied by h rxx h Hermitian plus rw inverse multiplied by y minus expectation of h times expectation of y. Expectation of x. Yeah. Now what information do we have? So this thing is 0 mean, so this goes to 0 and this also goes to 0. Another thing that we know is this RWW is 0 mean, this W is 0 mean with variance sigma square. So this means that this RWW will be sigma square I because it's IID. Okay, so we are considering these to be IID and IID. Yeah, let me write it. So it has a variance of sigma square and I. So this comes out to be H RXX H RXX H Hermitian plus sigma square I inverse multiplied by y. And this is your LMMSE estimate. So this is your least squares and this is your LMMSE estimate. Okay. Any questions? Okay, if there are no questions, then I'll go with the next question that I have. So what does it say? We need to find the ML estimate of A. To find the ML estimate of A in xn equal to A cos 2 pi fn plus phi plus wn, where this n ranges from 1 to capital N and this wn is Gaussian with 0 mean and sigma square variance. Yeah. So we need to find ML estimate. So basically what do we have? We have this vector x. We have this vector x which is basically x1, x2 and so on till xn. And this I can write as A times cos 2 pi f naught plus phi cos 2 pi 2 f naught plus phi cos 2 pi n f naught plus phi plus w1 w2 wn and yeah, can I forgot to mention these are IID. Okay, so what does your ML estimate say? So we need to find ML estimate of this. Okay, so what your ML estimate says? So we need to find A hat, which is argmax of A, and what is your argmax for? This is x comma A. So you need to first find this function fx given A, or rather this is your likelihood function that we need to find. Okay, so we need to find your f of x given A. Now you observe carefully if we need to find this PDF of x given a. So expectation of xn. So let me just do it. Yeah. So expectation of xn given. Okay. So given a, this quantity becomes constant. So this is something like, let's say if this is Cn, let's say this is Cn, then this is basically xn plus Cn, xn equal to Cn plus Wn. Okay, so yeah, we need to find this, and we have xn equal to a cos 2 pi f naught n plus phi plus Wn. So your expectation of xn given a will be equal to a cos 2 pi f naught n plus phi, because this is a constant now, plus expectation of Wn, and Wn is anyway 0 means. So this is your thing that we are having. Similarly, your variance of xn given a will be, now variance of a constant term is 0, and this term is anyway a constant factor, so we can just ignore it. And variance of this Wn is sigma square. So this is your sigma square. Now this is for all n. And another thing that you should note here, the only random variable given a is this Wn, and this Wn are IID for all n from 1 to capital N, which means that xn given a will be again Gaussian, independent, with means these and variance these. Okay, so now your f of xn given a will be 1 upon under root of 2 pi sigma square into e to the power minus xn minus this mean, that is a cos 2 pi f naught n plus phi square upon 2 sigma square. Okay, and your f of x given a will be product of n ranging from 1 to capital N, f of xn given a. Now this comes out to be 1 upon 2 pi to the power n by 2 into exponential, let me write 2 step by step. Yeah, add a page and do it on next page. Yeah, so you have f of x given a is equal to product of n equal to 1 to capital N, and let me substitute this value f of xn given a, so that will be 1 upon under root of 2 pi sigma square into e power minus xn minus a cos 2 pi f naught n plus phi square whole divided by 2 sigma square. So this term is getting multiplied n times, so I can write it as 1 upon 2 pi sigma square to the power n by 2. And now this term, I can take this product inside this exponent. So product of exponents will be e power summation of those factors. So this will be exp minus 1 by 2 sigma square summation n running from 1 to capital N xn minus a cos 2 pi f naught n plus phi square. Okay, so now what do we have is, we have this a hat equal to argmax over a of this factor of x given a. This is also equal to argmax of A of log of natural log of f of x given A. And why? Because your log is monotonically increasing function. And what do you mean by that? What do you mean by monotonically increasing function? So your log actually goes like this. So now if I take this x1 and this x2, so if x2 is greater than x1, then your f of x2 is also greater than your f of x1. So this is known as your monotonically increasing function, and log is one such. So if you are maximizing a monotonically increasing function, then it is equivalent. So if you are maximizing a function, let's say f, then it is equivalent to maximizing it inside a function or taking it as a argument of your log or any monotonically increasing function. So this becomes a valid argument. So now if we take this, then so what we can do is we can now differentiate this and set it equal to 0 at a equal to a hat. So now let us look at log of f of y given a, which is log of, I'll just take this and paste here. Yeah. So this is equal to n by 2 log of minus n by 2 log of 2 pi sigma square minus 1 by 2 sigma square summation n equal to 1 to capital N xn minus a cos 2 pi f naught n plus phi whole square. So now let us find this quantity. So in that situation, your first term here is independent of a, so this goes to 0 after differentiation with respect to a. Now if we consider this term, then this will be equal to minus 1 by 2 sigma square summation n equal to 1 to capital N 2 times xn minus a cos 2 pi f naught n plus phi multiplied by differentiation of this term, which is inside the square, that will be minus cos of 2 pi f naught n plus phi. And now we need to set it equal to 0. To set it equal to 0 for your when your a equal to a hat. So therefore we have, this gets cancelled, so we have 1 by sigma square summation n equal to 1 to capital N xn cos of 2 pi f naught n plus phi minus a hat summation n running from 1 to capital N cos square 2 pi f naught n plus phi, and this is equal to 0. So therefore now this thing is entirely outside the bracket, so this is anyway a positive quantity, so we can just take it to the right hand side and ignore it. So therefore we have this a hat is equal to summation n running from 1 to capital N xn cos of 2 pi f naught n plus phi whole divided by divided by summation N1 income one to capital N cos square 2 pi f naught n plus pi. So this is your ML estimate for A. Any questions? Okay, if there are no questions, then I'll go ahead with the next question that I had planned. So this is also a question on finding an ML estimate. So it says that if y equal to hx plus n and n is Gaussian with zero mean and variance sigma square, and let's say this h is known and we need to find the ML estimate of x. So in this equation, this h is a constant. We need to find ML estimate of this x, and this n is given as Gaussian um, with zero mean and variance sigma square. So now again what we need to do is we need to find this x hat, which is ML estimate, which will be again argmax of x of y given x. So now again we'll see that when your x is given, this term here is a constant. So if this term is a constant, this is only a function of a Gaussian random variable, linear function of Gaussian random variable, which means that this y will also be a Gaussian random variable. So now your y will be Gaussian with mean, let's say expectation of y given x and variance of y given x. Okay, so now what we need to find is we need to find this expectation of y given x, which is equal to expectation of hx plus n given x, which comes out to be equal to hx because expectation of n is equal to 0. Similarly, your variance of y will be equal to variance of this quantity here. Now again, this is a constant quantity and variance of a constant is 0, so only random variable present here is n. So therefore this will be equal to your variance of n, which comes out to be equal to sigma square. Okay, so therefore your y given x is Gaussian with mean hx and variance sigma square, and therefore f of y given x, that is your likelihood function, will be simply 1 upon under root 2 pi variance, that is sigma square, into e power minus y minus hx, that is your mean, square upon 2 sigma square. Okay, so this is your function. Now again, as the argument that we made earlier, this is equal to maximizing log of this, that is log of f of y given x. These two are equivalent statements because log is your monotonically increasing function. Okay, so now let us take your natural log of f of y given x. This comes out to be log of 1 upon under root 2 pi sigma square into e power minus y minus hx square upon 2 sigma square, which comes out to be minus log of 2 pi sigma square minus 1 by 2 sigma square into y minus hx. So hx square. So again we'll differentiate it. So we'll find differentiation of this likelihood function with respect to log likelihood function with respect to your x. So that comes out to be your first term is independent of x, so it will be 0 minus 1 by 2 sigma square into 2 times y minus hx multiplied by minus h, which is equal to 0. Now these are a constant quantities, like let's say at x equal to x hat we need to equate it to 0. So yeah, these are constant quantities, so we can just take them to right hand side, and what we are left with is y minus hx hat is equal to 0, and therefore your x hat is equal to y by h, and this is your ML estimate for x. Any questions? Okay, if there are no questions, then let's go ahead with the next thing. So okay, so here what do we have is, let yk equal to a plus wk, and a is greater than 0, it's given, and wk is Gaussian with 0 mean sigma square variance for all k ranging from 1 to capital N, and we need to find the ML estimate of a. So we need to repeat the same similar procedure. So what do we have here is yk equal to a plus wk, and given a, your y will be a Gaussian, so your yk given a is Gaussian with mean as expectation of a plus wk given a, comma variance of a is again constant, so just variance of wk. So this is basically Gaussian with mean a and variance sigma square. Okay, so therefore, and these wk's are again IITs, unless otherwise mentioned, everything will be IIT. Yeah, so your likelihood function of yk given a will be simply 1 upon under root 2 pi sigma square into e power minus yk minus a square whole divided by 2 sigma square. And if I stack these yk's in a vector, that is, if I take a vector y, which is y1, y2, and so on till yn, then since your wk's are IIT, then given a, these yk's are also IIT. Sorry, not IIT. Yeah, IIT. Yk's are also IIT because mean is independent of your k. So these are also IIT. So then f of y given a will be simply product of k running from 1 to capital N, f of yk given a. Okay, so now this comes out to be equal to 1 upon 2 pi sigma square to the power n by 2 into e power minus 1 by 2 sigma square summation k running from 1 to capital N by k minus a square. Okay, So this is your likelihood function. So again I'll write it. F of y given a is simply 1 upon 2 pi sigma square to the power n by 2 into e power minus 1 by 2 sigma square summation k running from 1 to capital N yk minus a whole square. Now I need to find ML estimate of this a. So your a hat will be argmax which is equal to argmax so this we are having here. Okay. So again we'll do this, that is differentiate this likelihood function, and at a equal to a hat we'll set it to 0. So therefore what do we have is, we'll differentiate the log of this. So therefore what we have is log of f of y given a will be equal to minus n by 2 log of 2 pi sigma square minus 1 by 2 sigma square summation k running from 1 to capital N yk minus a whole square. So this comes out to be, the first term is constant with respect to a, so it is 0, and second term will be 1 by 2 sigma square summation k running from 1 to capital N 2 times yk minus a multiplied by minus 1. So this comes out to be 1 by sigma square summation k running from 1 to N yk minus a. This is equation 1. So we need to set this equal to 0 when my a is equal to capital A. So therefore we have 1 by sigma square summation k running from 1 to capital N yk minus a hat equal to 0. Now this 1 by sigma square is a constant term, so I can just take it to right hand side and set it and just get it multiplied to 0. So what we have is summation k running from 1 to capital N yk minus summation k running from 1 to capital N a hat equal to 0. Now this a is independent of k, so I can just take it outside and you are adding 1 n number of times. So the second summation will simply lead to n times a hat, which implies that your ML estimate a hat will be equal to 1 by n summation k running from 1 to capital N by k. Any questions? This is your ML estimate for A. If you have any questions, please let me know. Okay, if there are no questions, then let's go ahead now. Yeah, so what we are having here is, let yk equal to a plus wk, and wk's are IID Gaussian 0 sigma square, k running from 1 to capital N. Now we have to find the Cramer Rao lower bound for A. This is the same setup which we have used in the previous question. In that question we had to find your ML estimate. However, in this question you need to find a Cramer Rao bound. Okay. So now let us just look back and see what is your Cramer Rao bound, Cramer Rao lower bound, CRLB. So what does it say? That if this regularity condition, that is expectation of dd theta log fy given theta is equal to 0, then your MSE, that is your mean squared error, will be greater than or equal to 1 by I theta, where this I theta is the Fisher information matrix, which is given by minus of expectation of d2 by d theta square log f of y given theta. So basically what we need to do is, first we need to check whether these regularity conditions are met. If this regularity condition is met, then we need to find your Fisher information matrix, which is given by this formula, and then we need to say that your mean square error will be greater than or equal to 1 by I theta. So this 1 by I theta is basically your lower bound over your mean square error or your error covariance. Okay, so first one, what we need to do is we need to check whether the regularity condition is true or not. So let me write it down. So step 1, check if regularity condition is true, that is whether expectation of differentiation of log of likelihood function is 0. And step 2 is find I of A, which is equal to minus of expectation of del 2 by del A square log of f of y given A. Yeah. And your MSE is greater than or equal to 1 by I A. Okay, so this is what you need to find. So let us first check whether your regularity condition is met or not. Now this is the same setup which we had done in the previous questions. It's exactly the same setup, and we had found out this factor here, that is the first difference of your log likelihood function. So this is what we had obtained. So this was 1 by sigma square summation k equal to 1 to n yk minus a. Okay, yeah. So let me add a page. So from equation 1 of previous question, we have del by del A log of f of y given A is equal to 1 by sigma square summation k running from 1 to capital N yk minus A. So what we need to find? We need to find expectation of del by del A log of f of y given A, which is, now the sigma square is a constant quantity, so I can take it outside, and this is expectation of summation k running from 1 to capital N yk minus A. Now this expectation is a linear operator, so this is equal to 1 by sigma square. So expectation of sum is basically sum of expectations, so this will be k running from 1 to capital N expectation of yk minus A. Okay, now if you look at this equation here, so your yk equal to a plus wk. So now if you look at yk minus A, That is, you find expectation of yk minus a, so that will be equal to expectation of wk. So your yk minus a is simply equal to your wk. So this I can write as 1 by sigma square summation k running from 1 to capital N expectation of wk, and these wk's are zero mean. These are zero mean and variance sigma square. So this expectation of wk is equal to this quantity. This quantity is equal to 0. So this entire summation now reduces to 0. So what we have is this term, this regularity condition, this expectation of del a log fy given a is equal to 0. This implies that regularity condition is met. So this we know. Okay. So if this we know, then we can go ahead and find out your Fisher information matrix, that is IA, which is given by this particular formula. So now we need to go to step 2. So we need to find IA is equal to minus of expectation of del 2 by del A square log of f of y given A. Okay, so this is equal to minus of expectation of del by del A of the first difference, which was 1 by sigma square summation k running from 1 to capital N yk minus A. So this comes out to be minus 1 by sigma square summation k running from 1 to capital N expectation of this yk goes to 0 minus del by del A of A, which is equal to 1, and the expectation of a constant is that constant itself. So this comes out to be minus 1 by sigma square into minus 1 summation k running from 1 to capital N 1. So this comes out to be n by sigma square. So your IA is equal to n by sigma square. Therefore your MSE is greater than or equal to 1 upon IA, which is equal to sigma square by n. So now another thing, if you observe, just a side note, that as your number of observations, that is as your n tends to infinity, your MSE or your IA tends to 0, or rather your lower bound 1 by IA tends to 0. This is an interesting thing to observe here, and this is your CRLB. Any questions? Okay, so if there are no questions, then let me go ahead with the next question. So yeah, so what does it say? It says that in the previous question, can you find an unbiased estimate of A? If yes, is it an efficient estimate, and what is its error covariance? Okay, so what we need to do is, in this particular question, we need to find an unbiased estimate of A. So we can make use of this Cramer Rao bound theorem, CRLB theorem. So what it says is, if I am able to write this d by d theta log fy given theta equal to I theta into gy minus theta, then directly I get my unbiased estimate, or my MVU estimate, such that your theta star is equal to gy and it achieves your covariance. The covariance achieves your CRLB, that is your MSE will be equal to 1 by I theta, and that's why it will be an efficient estimate. Okay, so if somehow we are able to write it in this form, then we are done. Then we are directly getting our MVU estimate. Okay, so what we need to do is, in this question, we need to try to write del by del A log of f of y given A as IA multiplied by some function of y only. This should be only function of y and nothing else. It shouldn't have A in it. Minus A. Then your A hat will be g of y. This will be efficient, and MSE will be equal to 1 upon IA. Okay. So now let us see this factor here. We had derived that. So this thing is equal to 1 by sigma square k equal to 1 to capital N yk minus A. Okay. So here del by del A log of f of y given A comes out to be 1 by sigma square summation k running from 1 to capital N yk minus A. Okay, this is what we are having here. So what we can do is we can just split this summation into two. So I can write it as 1 by sigma square summation k running from 1 to capital N yk minus summation k running from 1 to capital, okay, let me write it explicitly, k running from 1 to capital N A. So this is equal to 1 by sigma square summation k running from 1 to capital N yk minus n times A. Let me take n common, so that comes out to be n by sigma square multiplied by 1 by sigma square into summation k running from 1 to capital N yk minus A. Now if you observe carefully, this n by sigma square was this IA that we had obtained. This IA is equal to n by sigma square. So this thing here is your IA. Now if you observe this term is a function of y only. So this is basically your g of y. It can be function of other constant but not a function of A. So this term is your g of y. So this is equal to I of A multiplied by g of y minus A, which is the standard form which we were looking for. This is the standard form which we were looking for, and we have obtained that. So now by the definition or by the theorem, we have this A hat equal to gy. So this A hat will be equal to this particular quantity. So this A hat will be equal to 1 by sigma square summation k running from 1 to capital N yk, and this will have your MSE is equal to 1 by IA, that is sigma square by N, and this is, since it achieves your Cramer Rao Lower bound, since it achieves your CRLB, this is an efficient estimate. Okay, so let me just write it down again. So your A hat is equal to 1 by N summation k running from 1 to capital N yk. What we had seen that this is your MVU estimator. MSE is equal to sigma square by N. Again, this goes to 0 as my n tends to infinity, which says that it is a quite good estimate. So as my data is increasing, then I'm getting estimation error as 0. Okay, and its MSE is equal to this, and this is an efficient estimate. Another interesting thing you should note here is we had tried to find an ML estimate for the same thing in this question 4. We had tried to find out an ML estimate for the same setup in your question 4, and what we had found out, we had seen that my ML estimate was also equal to 1 by n summation k running from 1 to capital N yk. So this is basically your arithmetic mean, right? So this is the arithmetic mean of your yks. So what you can see is for this particular setup we are getting your a hat. So we are getting this is as equal to ML estimate also, which means that in this situation your ML estimate is also giving you an efficient estimate, which is your minimum variance unbiased estimate, and also it is achieving your Cramer Rao lower bound. Okay, so this is something interesting that you can note down for this particular setup. This may not be true every time. For few examples it will be, for few examples it won't be true. It won't be true in general. But in this particular case you're getting it like this. Any questions?
Madam? Hello? Hello?
So there are no questions, then let's go ahead for the seventh question for today. So what it says that if yi are Poisson distributed random variables with parameter lambda and I is ranging from 1 to capital N, these yi's are given lambda, these are IID, and we need to find the CRLB for lambda. So we need to estimate this lambda. So again we'll go by these two-step thing that we had discussed. So basically first we need to check if the regularity condition is true, and next thing we need to do is we need to find this Fisher information matrix, that is IE, and now here it will be I lambda. So let us do it step by step. So step 1, check regularity condition. Now what do you mean by Poisson random variable? So it is basically a discrete random variable. So if yi is Poisson distributed, then this f of yi given lambda will be equal to your e power minus lambda into lambda to the power yi divided by yi factorial. So this is the PMF of lambda, where this yi will take only integer values, rather positive integer, non-negative integer values. Okay, this yi will be like 0, 1, 2, 3, like all the whole numbers it can take. It can't take your negative integers. Okay, so now if these are independent, then your okay, so your f of y given lambda will be product of I equal to 1 to capital N f of yi given lambda, where your vector y is basically y1 till yn, as we have been doing it since previous few questions. Okay. So now what we need to, for your regularity condition, we need to differentiate the log likelihood function. So let us first find out your log likelihood function, that is log of f of y given lambda is equal to log of this product of I equal to 1 to capital N f of yi given lambda. Now log of product is basically sum of logs, so this comes out to be summation I equal to 1 to capital N log of f of yi given lambda. Okay. So your log of f of y given lambda is equal to summation I running from 1 to capital N log of this PDF, that is log of e power minus lambda into lambda to the power yi upon yi factorial. So now again these are product of some quantities, so I can write it as summation I equal to 1 to capital N minus lambda plus yi into log lambda minus log of yi factorial. Okay, so this I can write as minus n times lambda plus log of lambda into summation I running from 1 to capital N yi minus summation I equal to 1 to capital N natural log of yi factorial. Yeah. So this is what we are having here. So now we need to find del del lambda of log likelihood. Now the first term here will give me, this will give me minus n. Differentiation of log lambda will be 1 by lambda into summation I equal to 1 to capital N yi minus 0. So this comes out to be minus n plus 1 by lambda summation I equal to 1 to n yi. And for regularity condition, we need to find expectation of del del lambda log of f of y given lambda is equal to minus n plus 1 by lambda. These are constants, and summation I equal to 1 to n expectation of yi. And for a Poisson distributed random variable with parameter lambda, its mean and variance both are lambda. Okay, so in that situation, if mean and variance both are lambda, this quantity here will be equal to lambda. So this comes out to be minus n plus 1 by lambda into summation I equal to 1 to capital N lambda. So these lambda is a constant with respect to y, so I can just write it as minus n plus n times lambda by lambda. These two get cancelled, so what we have is minus n plus n, so this goes to 0, which means that my regularity condition holds. So my regularity condition is true. So now if my regularity condition is true, I can go ahead and then find out So now once we know this, we can go ahead and find out the Fisher information matrix, that is your I of lambda. So now we need to find I of lambda which is equal to minus of expectation of del 2 by del lambda square of log likelihood function, which is equal to minus of expectation of del by del lambda of first differentiation of this log likelihood function, which is basically minus n plus 1 by lambda summation I equal to 1 to n y, this quantity. So I can just take this and paste here. Yeah. Okay. So so differentiation of n with respect to lambda is 0. So this is 0 plus 1 by lambda's differentiation will be minus 1 by lambda square summation I equal to 1 to capital N by I. So this is again equal to 1 by lambda square expectation, or I can just take this expectation inside your summation by applying linearity of expectation property, expectation yi, and as we said earlier, this expectation of yi is this quantity is equal to your lambda. So this comes out to be 1 by lambda square summation I equal to 1 to capital N lambda. Now lambda is constant, so this comes out to be n lambda upon lambda square, which is equal to n by lambda. So therefore your I of lambda, that is your Fisher information matrix, comes out to be n by lambda, which means that your CRLB is equal to lambda by n. And what do we mean by that? That is your mean square error, your mean square estimation error will always be greater than or equal to n by lambda, which is nothing but your, what did I write here? So, which is, sorry, not n by lambda, which will be lambda by n, which is simply your I of lambda. Okay. Any questions? Okay. So if there are no questions, then let me go ahead and let's look at the next question that I have planned to cover. So what we need to do is, in the previous question, can you find an unbiased estimate of lambda? If yes, is it efficient? And what is the error covariance? So same question, it is very similar to your question 6 that you have solved. So we need to find, we need to make use of that Cramer Rao bound theorem. That is, what we need to do is, we need to try to write del by del lambda log of f of y given lambda is equal to I lambda g of y minus lambda, and here then your lambda hat will be gy, this will be minimum variance unbiased, this will be MVU estimator, this will be your efficient estimator, and this will have your error covariance as 1 by I lambda, which is your CRLB. And in previous question, your I of lambda was obtained as n by lambda. Okay, so this much information we have. Now we need to try to write this d by d lambda log differentiation of your log likelihood function in this given standard form. If you are able to do that, then we will be able to directly get your MVU or your minimum variance unbiased estimator. So that will just simplify our life a lot. So let's try to do that. So we have del by del lambda log of f of y given lambda as this. Okay. Now what we'll do is we'll try to take out, or let's do this. Let us try to multiply and divide by your IA. So we'll do this IA multiplied by 1 by IA. This will give me 1 into minus n plus 1 by lambda summation I equal to 1 to capital N by I. Okay, this we know. This we can do. This won't change our equation. Okay, so let's keep this IA outside and let's replace this 1 by IA. Let's replace this 1 by IA. Sorry, this is not IA, this is 1 by IA. Let's replace this 1 by IA by lambda by n. So let us replace this by lambda by n multiplied by minus n times 1 plus lambda summation I equal to 1 to capital N by I. Okay, so now again I can take this lambda by n inside and multiply it inside the bracket. So I have this IA multiplied by lambda by n into minus n. So this comes out to be minus lambda plus lambda by n into 1 by lambda. This comes out to be 1 by n summation I equal to 1 to capital N by I. Okay, so this is simply your IA multiplied by 1 by n summation I equal to 1 to capital N by I minus lambda. So what do we have? We can write this del by del lambda log of f of y given a is equal to IA times g of y minus lambda, where your g of y is equal to 1 by n summation I equal to 1 to capital N by I, as seen in this equation. Okay, so now we are able to write it in this standard form. So by definition, or by from this Cramer Rao bound theorem, your lambda hat will be equal to g of y. So therefore lambda hat is equal to 1 by n summation I equal to 1 to capital N by I. So again this is MVU, this has MSE as 1 upon IA, which is simply lambda by n, and again since it achieves your Cramer Rao lower bound, this is your efficient estimate. Any questions? Okay, so if there are no questions, then let's go ahead with question 9. So what does it say? A coin is tossed independently n times. A coin is tossed independently n times, and the observation yk is 1. If heads is observed, it is 0. Otherwise, for k ranging from 1 to capital N, and let p equal to yk equal to 1. That is probability that your yk is equal to 1. That is the probability that you are seeing a head. And now what we need to do is we need to find the ML estimate for this. Okay. So now what is happening is your yk can take two values. Your yk can be equal to 1 with probability p as mentioned here, or your yk can be equal to 0 with probability one minus p. Okay, I hope this is clear. And what we need to do is we need to find the ML estimate of p. That is, we need to find p hat, which is equal to argmax of p argmax of p f of y given, which is also equal to argmax of p log of f of y given. Okay. So what is your, so now these are independent tosses. So your f of y given p will be basically equal to product of k running from 1 to capital N f of yk given p. Okay. Why? Because your yks are independent. Now what is your f of yk given p? So for all k from 1 to till capital N, your f of yk given p, so this can take two values. So your yk can take two values, that is 1 and 0 with probabilities p and 1 minus p. So your PMF, that is f of yk given p, can take two values, that is p if your yk equal to 1 and 1 minus p if your yk equal to 0. Okay, so this will be equal to p if yk equal to 1. This will be equal to 1 minus p if yk equal to 0. Okay. Therefore, now let us look at log of f of y given p. This is simply equal to log of this term, that is product. So product of log of product will be simply equal to sum of logs. So this I can write as summation k equal to 1 to capital N log of f of yk given p. Okay. Now this will be equal to log p if yk equal to 1. So this I can write as yk times log p. So if yk equal to 0, this will go to 0. And this will be equal to log of 1 minus p if yk equal to 0. So this I can write as 1 minus yk times log of 1 minus p. Okay, so this term, this log term, I can write as log of f of y given p is equal to summation I equal to 1 to capital N yk times log p plus 1 minus yk times log of 1 minus p. Okay, so now this we can write as summation, or rather I can write it as log p summation I equal to 1 to capital N yk, sorry, not I, let me write it as k. Let's be consistent with it. K equal to 1 to capital N yk plus n times log of 1 minus p minus log of 1 minus p times summation k running from 1 to capital N by k. So this is simply n times log p minus this. Okay. So now I can combine these two. So these two I can write as log of p upon 1 minus p times summation k running from 1 to capital N yk plus n times log of 1 minus p. So this is what we are having. So this is your log of f of y given p. Okay. Now we need to find argmax of this. So for that, let us differentiate this term with respect to 0, with respect to p. So this will be del by del p of log of f of y given p. So in first term, you have 1 upon p divided by 1 minus p, or I can write it as 1 minus p by p multiplied by 1 minus p into differentiation of p, that is 1 minus p times differentiation of minus p, so that comes out to be minus 1 upon 1 minus p square, okay, into summation k running from capital Nyk plus n times 1 minus p multiplied by minus 1. So now this comes out to be, this p gets cancelled with this, so this is equal to 1. This 1 minus p gets cancelled with this, so this comes out to be equal to 1 upon p times 1 minus p into summation k running from 1 to capital Nyk minus n upon 1 minus p. So at p hat, this should go to 0. So therefore, at p equal to p hat, we have 1 upon p hat into 1 minus p hat summation k running from 1 to capital N yk minus n upon 1 minus p hat equal to 0. So I can take out this 1 minus p hat common and take it to right hand side, so that I can just simply cancel them out. So this goes to 0. So what I have is 1 upon p hat into summation k running from 1 to capital N yk is equal to n. So I can take this p to right hand side and take this n here. So what I have is your p hat is equal to 1 by n summation k equal to 1 to capital N by k. Now this p hat should be between 0 to between 0 and 1. But now again, if you look at this yk, this yk can take either value 0 or either value 1. So if you add zeros or 1 from 1 to capital N and then divide it by n, this quantity has to be between 0 and 1. So therefore I am not going outside the permissible range of this p hat. So this estimate is fine. This is a proper estimate that we are having, and this is the ML estimate for your p, for your Bernoulli random variable, which depends on your coin toss experiment. Any questions? Okay, if there are no questions, then let me go for the last question that I had planned to cover today. So it says that in the previous question, can you find an MVU estimate of P using CRLB? Okay. So again, this question we can solve by considering the two steps that we had seen. That is these two. Let us check if your regularity condition is true, and next find your IA, and step 3 is if I can write it in this form. So let me explicitly write them again. So what we need to do is step 1, check if expectation of del by del P log of f of y given P is equal to 0. If yes, go to step 2. In step 2, find I of P is equal to minus of expectation of del 2 by del P square log of f of y given P. And in step 3, write, or rather try, del by del P of log of f of y given P as I of P multiplied by g of y minus P. Okay, so these are the three things that we need to do. So let's start with our step 1. So let's start with step 1. So consider expectation of del by del P log of f of y given P, and his differentiation we had found out in our previous question, which was equal to 1 upon 1 minus P summation k equal to 1 to nyk minus n upon 1 minus P. So this we have as expectation of 1 upon P into 1 minus P summation k running from 1 to capital Nyk minus n upon 1 minus P. Now the only random variable here is your yk, so I can write this as 1 upon P into 1 minus P summation k running from 1 to capital N expectation of yk minus n upon 1 minus P. Now this yk, so this yk is equal to 0 with probability 1 minus P, and is equal to 1 with probability P, which means that your expectation of yk is equal to 0 into, it takes value 0 with probability 1 minus P plus 1 with probability P, so this comes out to be equal to P. So your expectation of yk is equal to P. So therefore expectation of del by del P log of f of y given p is equal to 1 upon p times 1 minus p summation k running from 1 to capital N p minus n upon 1 minus p. Okay, so now here again this p is constant, so this summation k running from 1 to capital N p is simply n times p. So this is equal to n times p upon p into 1 minus p minus n upon 1 minus p. So this gets cancelled. So it is n upon 1 minus p minus n upon 1 minus p. So this comes out to be equal to 0, which means that regularity condition is satisfied. Okay, so this condition is satisfied, so this is fine. So if that is true, then we need to go for step 2. And in step 2, what do we need to do? We need to find I of p, which is expectation of del by del p, or sorry, rather second differentiation, second derivative of log likelihood function. So this is equal to expectation of del by del p of your first derivative, which is this term, that is 1 upon p into 1 minus p into summation k running from 1 to capital N by k, the minus sign, sorry, yeah, the minus sign here, yeah, minus n upon 1 minus p. Okay, so now this comes out to be, let me just look at this factor. So this comes out to be yeah, so this comes out to be minus 1 upon p square into 1 minus p whole square multiplied by p into minus 1 plus 1 minus p into 1 into summation k running from 1 to capital N yk minus n upon 1 minus p square into minus 1 into minus 1. So this remains as it is. So now this comes out to be minus 1 up, this minus 1 remains as it is. This is basically 1 minus 2p so this comes out to be minus of 1 minus 2p whole divided by p square into 1 minus p whole square multiplied by summation k running from 1 to capital N by k minus n upon 1 minus p whole square. Okay, so therefore let us now find your IP. Therefore your IP will be equal to minus of expectation of minus 1 minus 2p upon p square into 1 minus p square into summation k running from 1 to capital N by k minus n upon 1 minus p whole square. Now again we have this yk as the only random variable, and this minus sign I can just take it outside. So what we have is 1 minus 2p upon p square into 1 minus p whole square into summation k running from 1 to capital N, expectation of yk minus n upon 1 minus p whole square. Okay, so this is what we are having here. Now again, this expectation of yk is simply equal to p, so this comes out to be 1 minus 2p upon p square into 1 minus p whole square multiplied by n times p minus n upon 1 minus p whole square. Now this p gets cancelled with this p, and I can take out n upon 1 minus p whole square outside, like common, so I can write it like n upon 1 minus p whole square. Inside the bracket it will be 1 upon 2p upon p minus 1. So there is something wrong here. Yeah, plus plus plus. So this comes out to be 1 upon 1 minus p whole square. I can take this one here, so it will be 1 minus p upon p. So this gets cancelled. So what we have is n upon 1 minus p times p. So what we have is my IP is equal to n upon p into 1 minus p. So this is the second step that we need to complete. So this was the second step. Now we have this Fisher information matrix, that is IP. Now what we need to do is we need to try to write this different first derivative of log likelihood function in this particular standard format. So let us try to do that. So now what we have is our step 3. So for that, again we'll look at this function. So this comes out, this we had obtained as this term, that is 1 upon p times 1 minus p summation minus n upon 1 minus p. So this what we have here is 1 upon p into 1 minus p summation k running from 1 to capital N yk minus n upon 1 minus p. So now we want this term, this n upon 1 minus p outside. So what we'll do is we'll take this n upon 1 minus n upon p into 1 minus p outside, like common. So that will be n upon p into 1 minus p inside the bracket. Now from first term we had taken out 1 upon p minus p. There was no n there, so we had to multiply by n and divide by n. So now what will be left with be k equal to 1 to capital N yk. Now this, in this term we had this n upon 1 minus p, but we didn't have this p, so we'll be left with p here. So now what do we have here? This is my IP. Let's say this is my g of y and this is p. So this we are able to write as IP multiplied by g of y minus p. And therefore from this equation what do we have? We have g of y as 1 by n summation k running from 1 to capital N by k, which is nothing but your estimate, that is p hat, and this estimate will be minimum variance unbiased, that is MVU estimate. This, it will have its error covariance as 1 upon IP, which is simply equal to p into 1 minus p upon n, and this will be equal to, yeah, and since it achieves Cramer Rao bound, this will be your efficient estimate. your MVU estimate of T, which is found using your CRLB theorem. Any questions? Any questions in any of the part which I have covered today? This was all I wanted to cover today. If you have any questions in anything that I covered, please feel free to ask. If there are no questions, you are free to leave the meeting. Thank you for attending today's session. Hopefully, I'll also take one more session next week, which will be somewhat like a summary session. Like I'll sort of revise all the content that was covered in the course, and that would be the last tutorial from my side. Thank you for attending today's session, and I hope you to see in the next session as well.